Welcome to the next in a series of introductory videos on chemical bonding and compounds. In the first video of this series, linked in the description below, it was shown that there are basically two types of compounds based upon two types of bonding. Bonding occurs between atoms that are either giving, taking, or sharing electrons. The giving and taking leads to an ionic compound, which will be what we will talk about today. Generally speaking, ionic compounds are made from metallic cations and nonmetallic anions. In all cases, the charges are going to cancel so that the compound is neutral. Also, through looking at the periodic table, there are several things that one already knows. For example, any elements in group 1 will have a charge of +1. Any elements in group 2 will have a charge of +2. In an attempt to get noble gas electron configuration, anything in group 6 will pick up 2 electrons to get to group 8 and become a -2. And for the same reason, anything in group 7 will pick up 1 electron and become a -1. The rest are determined based on what is known. How this is done, naming ionic compounds, is based on the fact that the names have to be unique, systematic, and completely descriptive. Naming compounds is governed by a group of people called the International Union of Pure and Applied Chemists, or IUPAC. This group was formed for safety, to make sure that anywhere you walk into a lab in the world, you know exactly what you're looking at on the front of every bottle. Interestingly enough, almost everyone on Earth already knows the basics of naming ionic compounds. Very simple common compound, NaCl, table salt, is sodium chloride. In that name, you essentially have everything you need to know about naming compounds. First, sodium is in group 1, has a charge of +1. Chlorine in group 7 has a charge of -1. So the name sodium chloride tells you the first rule. Ionic compounds have first names and last names. The cation, the positive ion, gets named first. The anion, the negative ion, gets named second. Within the cations, there are two possibilities. If the cation is in group 1 or group 2, one already knows what the charge is. Group 1 is going to be +1, group 2 will be +2, so it is simply needed to name the element. For any other element, you have to give the name, and you also have to give the charge following the name, in brackets, in Roman numerals. A similar set of guidelines goes for naming the anions. If the anion is a simple atom, such as a Cl with a negative charge, you've already seen the rule. Chlorine becomes chloride. You add the suffix IDE. We will see later in this video that there are other types of anions that exist that are molecules, groups of atoms covalently bonded together with a net negative charge. These you actually have to simply know the names and memorize them. And later on in this video, you'll see how to do that. So for simple compounds, how do you want to go about naming? First of all, again, what you already know. Group 1 is +1, 2 is +2, 6 is -2, 7 is -1. So I take a compound, CuBr2. If one looks on the periodic table, one sees that bromine is in group 7. Cu is copper. Bromine in group 7 has a charge of -1. Since it's negative, it becomes a bromide. Also, you will note that there are 2 Br minuses. the entire compound has to add up to a charge of 0. So the copper will have some charge, minus 2 will be equal to 0. So fairly obviously the answer is 2 minus 2 equals 0. So you have copper 2 bromide. Other compounds, MnO2 and Mn2O3. Both cases, Mn is the element manganese. Also common to both cases, oxygen, if you look on a periodic table, one realizes that it's in group 6, so it has a charge of minus 1. So first of all, a negative oxygen becomes an oxide. Both of these compounds, by naming, are manganese oxide. However, that does not go far enough because simply by looking at them, you see they have different formulas, therefore they need different names. The difference comes in balancing the charges. In the first case, I have 2 oxygens, which adds up to -4, which means the first compound is manganese plus 4, or manganese 4 oxide. In the second case, 3 oxygens adds up to -6, which means the 2 manganese have to add up to +6, which means each manganese is going to be +3, so the proper name for the second compound becomes manganese 3 oxide. In all cases, you're keying off the anion, which is going to be something that you know. Bromine in group 7 will be -1. Oxygen in group 6 will be -2. And also on the fact that the charges of the entire compounds have to cancel because the compound itself is neutral. The nice part about the IUPAC system is that it works both ways. If you have a formula, you'll know the name, but if you have a name, you can also determine the formula. For example, a compound, titanium 4 iodide. Again, looking at the periodic table, I have titanium, and I am told it is a +4. Iodine is in group 7, which means it's an I-. The lowest common multiple of 4 and 1 is 4, so in other words, for every 1 titanium, there are 4 iodides. So titanium 4 iodide is TiI4. If I look at another compound, vanadium 5 sulfide. The name tells me I have vanadium, symbol V, and that vanadium has a charge of +5. It also tells me that I have a negative sulfur in group 6, which gives me a charge of -2. So in this case, 5 and 2 give me a lowest common multiple of 10, which means for every 2 vanadiums, I need 5 sulfides, giving a formula of V2S5. Again, you're working on what you know, in this case, the anions, and with the name, what you are told about the cation. You're told what the cation is and what the charge is. The key point is that the entire compound has to add up to 0, so the pluses and minuses have to cancel out. The other type of anion mentioned, the molecular anion or oxoanions, are formed by different atoms sharing electrons in a covalent bond. Also, as the name implies, they all contain oxygen, and when all the bonds are formed, you wind up with a molecule with an overall negative charge. For these anions, it is essential that you simply have to, unfortunately, memorize them. 3 things need to be known: the name, the formula, and the charge. However, there is a system to naming them, which will be explained in the next couple of minutes. For example, a hydroxide ion is an OH with a -1 charge. This makes sense because hydrogen is in group 1 and has a charge of +1, while oxygen is in group 2 with a charge of -2. 1 minus 2 leads to the -1. Another common molecular anion is a carbonate, CO3 with an overall charge of -2. 3 oxygens add up to -6. The carbon has to have a charge -6 to give the overall -2 charge. That leads to a carbon with a charge of +4. And if you notice, carbon is in group 4, which means it has lost all of its electrons. Another common oxoanion, a permanganate. 4 oxygens add up to -8. Therefore, to give a molecule with a -1 charge, the manganese has to be +7, because 7 minus 4 times a -2, 7 minus 8, is a -1. A dichromate has 7 oxygens, adding up to -14. The 2 chromiums therefore add up to +12 to give the -2 charge, meaning that each chromium has a charge of +6. There's a systematic method for naming these ions based upon their oxidation state. This is especially shown for the oxoanions that are combinations of nonmetals and oxygens. Within group 5, oxygen can combine with nitrogen to form 2 molecules, an NO2 with a -1 charge and an NO3 molecule with a -1 charge. In the first place, 2 oxygens add up to -4, which means to get a -1 overall, the nitrogen has to be +3. For the second molecule, 3 oxygens add up to -6, which means to get the overall negative charge, the nitrogen has to be +5. The system devised says that the molecule with the lower charge gets the suffix ITE, the higher charge gets the suffix ATE. So NO2 -1 with a +3 charge on the nitrogen becomes a nitrite. A +5 charge on nitrogen in NO3 -1 becomes a nitrate. Staying in group 5, phosphorus and oxygen also give 2 combinations, a PO3 -3 and a PO4 -3. In the first case, 3 oxygens adds up to -6, which means to give the -3 charge, the phosphorus is +3. In the second case, 4 oxygens add up to a -8. The overall -3 charge gives a phosphorus +5. 3 is lower than 5, so PO3 -3 is a phosphite, while PO4 with a -3 charge becomes a phosphate. Group 6. Sulfur and oxygen, both in group 6, will combine to give 2 combinations once again, an SO3 -2 and an SO4 -2. In the first case, 3 oxygens adds up to -6, which means the sulfur is a +4 to give an overall charge of -2. In the second case, 4 oxygens add up to -8, which means the sulfur has to be a +6 to add up to a -2. The lower charge of +4 therefore becomes a sulfite. The higher charge of +6 becomes a sulfate. In group 7, with oxygen, the following applies to chlorine, bromine, and iodine. You have, first of all, using chlorine as an example, a molecule ClO2 with a -1 or ClO3 with a -1. 2 oxygens for a -4 means the chlorine in the first case has to be +3. For the second molecule, 3 oxygens add up to a -6, which means the chlorine has to be a +5 to give an overall -1 charge, giving a chlorate for a Cl2- and a chlorate for a ClO3-. However, in group 7, you have 2 other possibilities. You can have a ClO-1 or a ClO4-1. In the first case, 1 oxygen is a -2, which means the chloride has to be +1 to give a -1 charge overall. In the second case, 4 oxygens add up to -8, which means the chlorine has to be a +7 to give a negative charge. I now move to prefixes. The lowest possible charge gets the prefix hypo, so ClO-1 becomes a hypochlorite. The highest possible charge gets the prefix per, which means ClO4- becomes a perchlorate. Again, this applies to chlorine, bromine, and iodine in group 7, all of which will form 4 possible oxoanions combining with oxygen. Looking at the one gets an indication of the meaning oxidation. If I look at the group 7s, nitrogen and phosphorus, I have 2 possible choices, +3, +5. Sulfur gives me a +4 or a +6. In group 7, I can have +1, 2, 3, 5, or 7. First thing to notice is the gap. Between 3 and 5, 4 and 6, 1 and 3, 5 and 7, there is always a charge of +2. Oxidation specifically means increasing the positive charge because adding a negative oxygen requires a positive charge to balance it. The oxidation number is therefore the positive charge on any given element, +3, 5, 7, 6, whatever that number is. The other thing to notice, within group 5, your 2 choices are +3 or +5. Group 6, your choices are +4 or +6. Group 7, 1, 3, 5, and 7. In all cases, the highest oxidation number matches the group number. The number of outer shell electrons are all that can be either given or taken away, so the highest oxidation number is going to be the number of electrons indicated by the group number. Naming oxoanion compounds is no different than naming compounds where the anion is an atomic anion. For example, given a formula, FeNO2 3. A little bit of studying, I have iron, And I now know that an NO2 is a nitrite, and it specifically has a -1 charge, so it's an NO2 minus 1. So, if I have 3 of them, and the entire compound adds up to 0, that means the ion has to be +3, and I have an ion 3 nitrite. This was determined because I knew that an NO2 was an NO2 minus 1, and its name was a nitrate. Similarly, if I am given a name, sodium carbonate, notice there's no number after sodium. That's because, looking at a periodic table, I know sodium is in group 1 and it has a charge of +1. I also know a carbonate has a charge of -2, which means there's going to be 2 sodiums for every 1 carbonate. So the formula for sodium carbonate, based on the name, is Na2CO3. These are the rules as to how ionic compounds are named and how you can use the name to determine what compound you are actually dealing with. In the next video in this series, we will see how these ionic compounds are put together, what their structures are, and how that indicates how they will react. Thank you very much, and I hope you found this useful.